All right, right now we're going to do ripple adders and signed adders. A signed adder is when you're adding negative numbers. A ripple adder is a chain of adders, just like right here in this image. You see these this adder, this adder, this adder chained together. We were previously doing with our truth table. There's our two inputs, A and B, which are going to be these inputs here, X and Y. Excuse me. There's our carry in. The carry in is what's going into the adder. The carry out is what's coming out. There's the sum. There's the sum here. So let's do a ripple adder and then in Verilog, and then we're going to do a signed adder, and then I'll prove it to you mathematically how these how they work. So let's start with the ripple adder right here. How would you code that? Okay, so we have our two inputs. Remember, they're going to be the A and B. They're going to be 8-bit, two 8-bit ripple adders, and we need a carry out. The carry out handles the extra bit if you have too many bits to add. So here's our extra carry out bit and the sum. Now we're using continuous assignment. This is combinational. So assign sum equals A plus B. Did something wrong here. Output. There. So there's your ripple adder. Now let's do our signed adder in Verilog. Now we have now we have an overflow. To handle the carry bit, unlike the ripple adder. Now for this, we take the most significant bit of A and compare it to bit 7, and we see if it's equal to the most significant bit in B. We AND those together. Take the sum, the most significant bit of the sum, and compare it to the most significant. Make sure it's not equal to the most significant bit of B. That should be brackets. Sign sum and in. Sum 7. Oh, here it is. Okay. Sorry, it took a minute. Now let's prove that. So we have these two 8-bit signed numbers. We're going to add these together. I did this before, so I know it's 16. But since the positive, this here is positive, and this here, excuse me, it's 1, and this one's 0. This is negative. This is a positive number. So when we have a positive note, excuse me, when we have 1 as the most significant bit, that means it's a negative number. This is a positive number because it's 0. So 1 MSB is most significant bit. You have to invert all the numbers, add 1, and make negative. So let's do that. So you have, that's 4 zeros, and then 1, 2, 3, 4. 1, 1, 1, 1 is 16 in decimal. Let's make this smaller. Wider and smaller. So yeah, that's 16 in decimal. And then B is equal to $1,000. Oops, I forgot to do something. 111. I was wrong. Sorry. That's 15. It's 15. Add 1. Make it negative. Always forget to that. So it's negative 16. And 16 is so that's 16 in binary. Negative 16. 16, but this is a signed number, so it's negative. Now B, we're adding this. It's also 16. So, but this is positive because this here was 0. So you have 16 plus 16. Negative 16 plus 16 is 0. 1, 2, 3, 4, 5, 6, 7. But we don't have to change it because it begins with 0. So now we use our formula here for overflow. Sorry. That's our formula for overflow. So we have A to the 7th, not A to the 7th, the most significant bit of A, which is that's A, that's B, okay. A's is 0. B is 0. Sums is 0. Now we use this formula. Is A equal to A to this? Is A and B equal? True. 1. Is sum and A not equal? That's 0 is not equal to 0. That's false. Is 0 not equal to 0? False. 0. Just remember, this is A and B is 0 and 0. A is equal to B. That's true. 0 is not equal to 0. It's false. So 1 and is 1 and 1, 0, no overflow. That's it. There's no overflow. If there was overflow, this would be 1. That would be overflow.